So let's begin today by looking at the hydrosphere and the overall hydrologic cycle, beginning with running water. Now, if you look at the distribution of Earth's water, by far most of the water on Earth, 96.5% of it, is stored in the oceans, and the remaining 2.5% is considered fresh water. If we look at the distribution of just the freshwater portion, we find that most fresh water is stored in glaciers and ice sheets, 68.6%. About 30% is stored in groundwater, and a little over 1% is stored as surface water and other fresh water. If we just focus on the surface water, we see that most of the surface water is contained within snow and ice, about 73%. About 20% is stored in lakes, a little over 3.5% as soil moisture, and about 2.5% as swamps. The remaining water, less than 1%, is stored within the atmosphere as biological water and as rivers. So rivers constitute only a very, very tiny percentage of all the surface fresh water on Earth, but even so, streams and rivers tend to be very important geologic agents that we should consider. I assume that water and biological life just, the water stored in our bodies for metabolic purposes. I assume that's what they mean. Particularly plants. Plants undergo transpiration. That's part of the hydrologic cycle we'll look at. Now, the water reservoirs on Earth are mainly the oceans, the atmosphere, ice and snow, vegetation, streams and rivers, lakes, and groundwater, of which we're mainly going to focus on streams and rivers today and consider groundwater in the next chapter, and finally move on to oceans as the last lecture topic. The hydrologic cycle is a way of tracing the cyclical movement of water through these various reservoirs. And the water is transferred from one reservoir to another, for example, from the oceans into the atmosphere or atmosphere onto the land surface, mainly by way of evaporation, precipitation, transpiration, which is the release of water into the atmosphere by plants, in addition to ground infiltration and finally surface runoff. And if you look at the overall schematic diagram of the hydrologic cycle, we see that we account for the volume of water being transferred from one reservoir to another. And we're assuming that there's a constant volume of water on Earth, and we're simply moving it around from one place to another. But for today, we're going to mainly focus on surface runoff, a very small component of the overall hydrologic cycle, but still a very important one. Now, running water originates as rain and melting snow. Water that does not infiltrate into the ground becomes runoff. Runoff begins in what is known as sheet flow, as shown in the lower right-hand block diagram. And from there, sheet flow develops into tiny channels that are called rills. The rills, in turn, will flow into gullies, and eventually the gullies will carry water into nearby streams and rivers. So rivers and streams are bodies of water that flow down slope within restricted passageways referred to as channels, while first of all transporting detrital particles, sediment, and also dissolved substances, the products, in other words, of chemical and mechanical weathering. Streams also erode channels in which they flow. They're very important erosional agents, depositing sediments in certain places, and overall shaping the varied landscapes that we find on land surfaces today, particularly the hills and the valleys, the basins, and so on, particularly drainage basins that we're going to look at in a little bit more detail. So streams are vital geologic agents that carry most of the runoff that goes from land to sea, and in the process transports billions of tons of sediment to the oceans each year, and can also carry small amounts of soluble ions, salts, into the sea while shaping the overall surface of the earth. We're going to look at stream action, in particular stream erosion, in a little bit more detail. But this table lists the world's largest rivers ranked in order of discharge. The Amazon River in Brazil is by far the largest, followed by the Congo River in Africa. Of the top 10 world's largest rivers, only one, the Mississippi, occurs in the United States, and the Mississippi is ranked number 7. Let's begin by looking at stream flow, in which we can distinguish laminar flow versus turbulent flow. Laminar flow is characteristic of slow-moving streams, whereas turbulent flow is characteristic of faster-moving streams. In laminar flow, the streamlines tend to follow roughly parallel paths, whereas streamlines in turbulent flow tends to be erratic with swirling motions. What's more, turbulent flow may exhibit whirlpools and eddies, and for the most part constitute rapids and things of that nature. Here, for an example, is laminar flow. If you look at the photograph on the right, we see that the water appears to be standing still, but actually is probably flowing very, very slowly. And we see in the upper left-hand corner that the flow surface in this cross-section tends to be, for the most part, relatively flat. And within the stream bed, we can get a little bit of a turbulent action, creating mainly ripples and small-scale cross-bedding for the most part. On the other hand, turbulent flow is characterized by a very rough flow surface, higher velocity water flows. Stream bed deposits tend to be large ripples and even dunes with well-pronounced cross-bedding. And this type of flow is characterized by rapids, for example. Now, briefly looking at stream channels, the size and shape of its channel cross-section is a function of several different factors, which include the overall stream gradient, or basically the slope of the stream, in addition to the surrounding rock type, whether the rocks are easily eroded or very resistant to erosion. The stream could be even flowing through sediment rather than bedrock. You also have to consider the overall volume of the water that the stream is carrying. This is known as discharge. The most efficient channel, for the most part, is one with the least perimeter for its cross-sectional area. And this is shown in this pair of block diagrams. In the upper diagram, we find that large streams usually have widths many times greater than their depths, and the Mississippi River is a good example of this, whereas small streams may be as deep as they are wide. But if you compare these two figures, notice that the wetted perimeter of a wide, shallow channel is about 12 units, whereas the wetted perimeter of the narrow, deep channel is about 9 units. And in both cases, the maximum water velocity, mainly within straight segments of these channels, tend to occur in mid-channel near the surface. As we approach the walls and the base of the channel, the water is subjected to greater frictional forces with the channel margins, and as a result tends to slow down. This is why maximum velocity tends to be mid-channel near the surface, because this is where the water experiences the least amount of frictional resistance with the channel wall. Now, average stream velocity is typically determined using measurements from several spots across the stream. One way to measure stream velocity is basically this sounding weight that has these little conical cops that spin within the stream flow, and obviously the faster the stream flow, the faster those little cups will spin, and then that data is recorded by these stations situated throughout the United States. As a matter of fact, the U.S. Geological Survey operates and maintains nearly 7,500 stream gauging stations throughout the country. And notice that there's a cable that extends across the stream channel, and this allows the flow velocity to be measured in several places across the stream. That for the most part just spins in response to the moving water. On the other hand, the newest meters utilize Doppler radar. And many of these gauging stations are also associated with a stilling well, which measures the water level within the stream. And as the water level rises or falls, this information is sent via satellite to various agencies that monitor this type of data. There are several factors that control the way that the stream behaves, including the gradient, the channel cross-sectional area, typically expressed as square feet or square meters, the average velocity of the water in feet per second or meters per second, as well as the discharge expressed in cubic feet per second or cubic meters per second, and also the overall load of sediment that the stream is carrying, oftentimes expressed in kilograms of sediment per cubic meter of water. The stream gradient, as seen by this remarkably detailed figure I constructed, is simply the altitude of the stream at point 1 minus the altitude of the stream at point 2 divided by its overall horizontal distance between the 2 points. So stream gradient is a number, and obviously the higher the number, the steeper the slope. Here in this profile of the Kings River in California, the stream head is defined as the point where the stream originates, whereas the mouth is where the stream empties into a large body of water. And for the most part, we see that the stream gradient is typically steepest near the head and flattens out as it approaches the mouth, so that this gradient is near horizontal by the time it enters a large body of water, like a lake or the Gulf of Mexico, or maybe a cup of coffee or whatever. No. Jeez. Now a stream discharge is a measure of the total volume of water carried by the stream as measured from a particular location. And typically discharge is expressed in units of cubic meters per second or cubic feet per second of water. A is the cross-sectional area of the channel, the width times the average depth, and V is the overall velocity of the water at that particular measuring station, generally expressed as meters per second or feet per second. So we see that the overall discharge of a stream is simply the cross-sectional area times the average velocity of the water. Here, for an example, is a unrealistic cross-section showing a stream with channel with near 90-degree bends. But we take this configuration just to show a simple calculation of discharge. Here, the height of the stream is about 1.2 feet, and the width is 59 feet. Obviously, this is not to scale. And the velocity is 1.5 feet per second. And so by calculating the cross-sectional area, which is 70.8 square feet, multiply that by the velocity, we get a stream discharge of about 106 cubic feet per second. This is the river at average level. But then here we have the same channel at high level, where the cross-sectional area is now 3.1 feet times 82 feet, which gives us a 254 square feet. The figure shows cubic feet. That's wrong. It's 254 square feet cross-sectional area. And we take that value in turn and multiply it by the stream velocity of 3.5 or 3.1 feet per second, and we get a discharge of 788 cubic feet per second. Okay, so obviously the discharge is quite a bit greater during near flood stage compared to the average. We can distinguish three zones of a river system: the headwaters, the zone of transportation, and finally the zone of deposition. The headwaters, again, is where the stream originates, and typically this occurs in areas of higher elevation and more rugged terrain. And as a result, extensive erosion within the head area of the headwaters produces lots of sediment, which then enters the stream and is carried downstream. So we can regard the headwaters as basically a zone of sediment production as a result of extensive erosion. Further downstream, we enter the zone of transportation. This is mainly the stretch where sediment is carried by the stream from higher towards lower portions. Also, at this point, within this stretch, there's a lot of tributaries entering the stream, adding more water and sediment to the overall stream. And then finally, the stream reaches a large body of water like a lake or a large gulf, something of that. And at that point, most of that sediment is deposited as possibly either a delta, or at the base of mountains we could get alluvial fans, things of that nature. Here's a graph showing the changes in stream properties from headwaters to the mouth. And notice that as we go from the head to the mouth of the stream, the overall channel slope decreases, as we saw before, Stream gradient is steepest near the headwaters and flattens out near the mouth. Also notice that the channel roughness decreases from the headwaters towards the mouth. On the other hand, the discharge, the channel size, and also the flow velocity all increase as we go from the headwaters to the mouth. The increase in discharge is due to tributaries, again, entering the main stream further downstream, adding more water to the overall discharge. And in order for the stream to accommodate the greater discharge, the stream will widen and deepen its channel and also increase the flow velocity in order to accommodate that higher discharge. So let's start at the headwaters and look in more detail at stream erosion. Increasing the stream velocity can result in erosion of the channel, and when the flow of water is sufficiently strong, the water can dislodge and lift particles within the channel. The stream velocity, in turn, can increase due, for example, to increasing discharge, such as after a heavy rainfall. And another way of increasing the stream velocity is simply by narrowing the stream channel. Now here for an example, this shows a landslide locally narrowing the stream channel. And notice that where the stream is flowing around the landslide, that velocity increases. This increasing velocity in turn can result in erosion and gradual removal of the landslide debris. In this figure, the stream velocity is relative to the length of the arrow, so the longer the arrow, the faster the stream flow. Here's another example of a bridge pier, which increases the velocity of the stream and sometimes accelerates erosion next to the piers, again, as a result of constricting the channel. A sufficiently strong flow of water can dislodge and lift particles in the channel. And these loosely consolidated particles are lifted by either abrasion or dissolution, where the material actually enters as ions into the water. And in general, stronger, faster currents will lift particles more effectively. Here's some examples of stream erosion, like these potholes formed by the rotational motion of swirling pebbles. In other words, when this bedrock is covered by flowing water, sometimes these pebbles will get caught up within these little depressions and kind of act like little drills and slowly quickly spin around and literally deepen those depressions within the bedrock. Here's a very deep channel which experienced extensive downcutting due to stream erosion. Streams can also erode side to side, resulting in these undercut banks. And when the undercut bank is eroded back far enough, the overhanging material will then collapse into the channel itself and be carried away by the stream. Now, a stream will transport material three different ways: as bed load, suspended load, and dissolved load. Now, in bed load, coarser particles are mainly moved by rolling and sliding along the stream bed, whereas the finer particles are carried in suspension as a suspended load, mainly clay particles. And we also have the dissolved load, which consists of dissolved chemical substances ions such as bicarbonate, calcium, potassium, and so on. And here's a cutaway view of a stream showing these three different ways that the stream transports a material. Notice that the sand, gravel, and boulders are mainly transported as bed load by sliding and rolling. Sometimes the particles will be picked up temporarily, then dropped again, and are carried in a bouncing pattern downstream in what's known as saltation. The suspended load, on the other hand, are the particles that are small enough to be carried in suspension, mainly silts and clays. And then the dissolved loads, which are largely invisible, are simply the ions in solution. And here's some examples of bed load. Obviously, these are photographs during times when the discharge is very, very low. But other times, these larger particles can actually be transported further downstream, mainly by sliding and rolling along the bed. Now, there are two measurements that we can consider, stream capacity and stream competence. Stream capacity is a measure of the maximum load a stream can transport. And in general, increasing discharge increases the overall capacity of a stream. Competence, on the other hand, is an indicator of the maximum particle size that a stream can transport. And competence is determined by the stream velocity, such that greater velocities can carry larger particles in suspension, and also as a bed load. Here's a log-log plot of suspended sediment load in tons per day versus discharge. And notice in general that streams with higher discharge can carry greater sediment load, which is intuitively obvious, but they have to pretty much use log-log plots to get this scattering of data to line up in any particular fashion. Now, base level is the lowest point to which a stream can erode, and there are two general types of base level. One is ultimate, which is global sea level, but we can also have local or temporary base levels, such as a resistant rock layer, lakes, dams, and things of that sort. A waterfall, for an example, like Niagara Falls, is a good example of a local base level. And over time, Niagara Falls is gradually eroding back towards Lake Erie, as explained in this particular figure. But let's start out with a profile of a landscape with this resistant bed. And here we have two different stream profiles. One is the dashed line, which represents the profile of the stream if the resistant rock layer did not exist. But because of that resistant bed, we have two different gradients. We have an upstream gradient that's adjusted to the local base level, which is the waterfalls. And downstream of the resistant bed, we have another stream gradient that's adjusted to ultimate base level, which is the sea. Over time, the stream will gradually downcut and erode back that resistant bed, reducing the local base level. And in the process, the downcutting will lower the overall upstream gradient. At the same time, the sediment will raise the downstream gradient as these stream adjustments occur. Ultimately, with the local base level removed, the entire stream profile is eventually adjusted to ultimate base level. And at that point, we get what's known as a graded stream. Okay. Now here's an example of a temporary or local base level. We see in the upper block diagram the profile of the stream before, which has been adjusted to ultimate base level. But then with the construction of a dam and impounding of water behind the dam in the reservoir, we see that a new stream profile is created through deposition of sediment. In other words, the stream has to raise its overall profile and gradient in order to accommodate the new temporary base level. Oops. Damn it. Now, changing the conditions will cause readjustment of the stream activities. For example, raising the base level causes deposition, whereas lowering the base level causes erosion as the stream downcuts to reach its new base level. So by definition, a graded stream has the correct slope and other channel characteristics that are necessary to maintain the velocity required to transport materials supplied. And a graded stream, on average, is neither eroding nor depositing material. That's not quite true, because there are times when discharge increases and erosion accelerates, whereas other times where the stream discharge drops and there's sedimentation. But on average, the graded stream is neither eroding nor depositing material. However, a change in one characteristic of a stream will cause the stream to modify its channel in order to offset the effect. For example, a stream will downcut and deepen its channel if the land is uplifted or sea level drops in order to achieve the new base level. A stream will also widen or deepen its channel to accommodate increased discharge. And the stream will deposit sediment if the discharge decreases or sea level, in other words, base level, rises. So let's move on and look in more detail about deposition of sediment by the stream. When stream velocity decreases, this is generally due to the reduced discharge, or possibly widening of a channel can also reduce the stream velocity. Velocity decrease in turn results in sedimentation, where the competence is reduced and sediment begins to drop out of suspension. As a result, we get deposition of stream sediments, collectively referred to as alluvium. And this alluvium occurs as both channel deposits and also floodplain deposits. Here, for an example, we see in the foreground a widening channel. And this widening is resulting from the channel passing, or the stream passing from hard to soft rock. And with the widening of the channel, we get deposition of these bars in the mid-channel. And this just illustrates how this is the result of the slowing down of the stream velocity as a result of this channel widening. Channel deposits exhibit a wide range of grain sizes, anywhere from gravel to sand to silt to clay, depending upon the stream. Bars, for example, are channel deposits that occur within and between divided channels, particularly within braided streams that we'll look at in more detail. Point bars occur along the banks of meandering streams where there are bends. We'll look at point bars also. Deltas, in turn, are deposits that form where a stream enters a large body of water like a lake or a gulf, whereas alluvial fans accumulate along steep mountain fronts. First of all, in the case of floodplain deposits, sediments deposited on a floodplain during floods is generally finer grain, typically silts and clays, relative to channel deposits. And we can even have formation of natural levees that are constructed adjacent to the stream channel by successive floods over many years. Here, for an example, we see in the right a sequence of frames showing the development of natural levee with successive flooding events. Notice that when a flood occurs and the stream spills over its bank, the coarsest sediments are deposited adjacent to the stream channel, whereas finer sediments are carried off into other parts of the floodplain. With successive flooding of events, more and more coarse sediments are deposited adjacent to the channel, resulting in the buildup of natural levees over time. Deltas, on the other hand, form when a sediment-charged stream enters the relatively still waters of a lake, an inland sea, or ocean, and dumps its sediment load. And in the bottom series of figures, notice that as the stream deposits sediment, its channel extends further out into the large body of water. And this mainly is the result of a reduction in the stream gradient when it enters that large water body. And with the stream velocity dropping, the stream just literally just dumps its sediment in place. And over time, the stream channel will extend deep further out into the large body of water, and even shift direction over time, constructing these various distributaries that tend to fan out in all directions, depositing more and more sediments as a result. So that over the course of thousands and thousands of years, extensive delta deposits can extend far out into the large water body. Here, for an example, the Mississippi River, as we see in this figure, has built a series of shifting subdeltas over the past 6,000 years. And these different numbered lobes are just different times, different parts, different regions where deposition was actively occurring. And once the lobe gets significantly filled with sediment, the distributaries just simply shift direction and start dumping sediment in another part of the region. And over time, these shifting subdeltas create this large Mississippi Delta that's continuing even today to extend further out into the Gulf. The present site of the deposition is that Birdfoot Delta that's labeled lobe number 7. Other places we can get what's known as a triangular delta, particularly in places where there's a lot of reshaping of the delta by strong waves and currents of the large water body, as for an example occurs in the Nile Delta. So a large determinant as to the shape of the overall delta is whether sedimentation is fast enough to counteract any reconfiguration of the coastline by the large water body. Alluvial fans, on the other hand, accumulate along mountain fronts where sediment is deposited as the mountain stream experiences a sudden decrease in gradient and hence velocity when flowing onto a flatter surface. And again, because of the abrupt drop in stream velocity, the sediment is simply dumped in place. And here's some photographs of alluvial fans. These things occur, again, at the base of mountains where mountain streams, discrete gradients of mountain streams suddenly encounter the relatively flat terrain of an adjacent valley, as, for example, occurs along the Basin and Range region of Nevada, places like that. Anyway, any questions?